Hello everyone, this is Oguz from LBNL, from Computational Research Department, and the subject of this talk is going to be about the parallelization of the Markov clustering algorithms for systems with GPU support. So the Markov clustering algorithm is a very popular algorithm, especially in bioinformatics, and it is used to cluster several different networks, graphs in that area. I'll be focusing on the protein similarity networks, which are useful structures for detecting protein families. Proteins in a family share significant circular similarity along other features such as similar three-dimensional structures or functions. So this is useful. Detection of protein families is useful in assigning functions to the family members by the help of the well-characterized proteins within a family. They're also significant in comparative genomics, and they provide valuable evolutionary insights. One way to discover protein families is through protein sequence clustering. We can compare sequences and assign a similarity score, and then use that information to cluster the network. This network can be seen as a matrix. Here's a pipeline to form a protein similarity graph. Here at the left, we have protein sequences, which consist of a number of bonded amino acids. Here we only make use of the sequence information. There are other useful structures of proteins we don't make use of. These are usually dimensional information. From a given set of proteins, we select pairs on which we want to run alignment. Here there are several variants, generally grouped under the global or the local alignment. This will produce us a similarity measure, which we can then use to establish how similar those pairs are. Usually we filter out pairs that we do not need or that do not meet certain criteria. This finally leads us to the protein similarity graph. And this is the part I'm going to focus on, how to cluster this protein similarity graph. The Markov clustering algorithm aims to discover clusters by simulating flows on the networks. By performing random walks on the graph, it relies on the observation that the number of higher length paths between two arbitrary vertices in the graph is large if the vertices are in the same dense cluster, and small if the vertices are in different clusters. And by building on top of this observation, it argues that a random walk is likely to stay in a dense cluster until many of its vertices are visited. So there's a distributed memory implementation of this Markov clustering algorithm called HipMCL, which is also developed at the LBNL. So it consists of two successive phases. In the expansion phase, the first step enables connecting to different regions in the graph. And one step of this random walk can efficiently be implemented as sparse matrix squaring, which is a special case of the sparse matrix matrix product, which, or in short, SPGM. The inflation step, on the other hand, aims to strengthen the intercluster connections and weaken the intercluster connections. And it also determines the finer granularity of the clusters. We inflate because the flow should be easier within dense regions than across sparse boundaries. So this can also be expressed as true linear algebra. So it's just an element-wise operation on the entities of the matrices, entities of the matrix. So a little bit more information about the HipMCL. So this, as I mentioned, this is distributed memory parallelization of the Markov clustering algorithm. It takes advantage of the aggregate memory to cluster very large networks. It relies on sparse matrices to store information and operations on sparse matrices to manipulate this information. And it makes use of combinatorial BLAS, a parallel graph library for graph analytics. And this library supports hybrid MPI plus OpenMP type of parallelization. There are several key features of HipMCL to attain scalable performance. Among the most important of them are it makes use of a two-dimensional process grid to achieve a better communication performance. Another important feature is the phase execution model in order to be able to scale huge networks. In this memory efficient expansion and pruning, it processes a subset of columns instead of comparing the output all at once. So because the networks are huge, we do not have enough memory to store the entire output. It uses sparse summa for distributed multiplication. This algorithm is a two-dimensional matrix multiplication algorithm. So that's in line with the two-dimensional process grid we use. Finally, at the end of this process, a connected component algorithm is run to get clusters. Again, this is expressed through fast linear algebra primitives and which are usually centered around sparse matrix vector multiplication. So these are the main components of the MCL algorithm. As I mentioned, expansion and pruning and inflation. So the expansion and pruning is performed in two successive steps. First, we estimate the memory we need for the expansion so that we can divide the output matrix into column stripes. So this involves a dry run of the numeric multiplication, which is indicated as a symbolic multiplication. And the expansion phase then proceeds in phases. So it consists of a number of sub-steps, so here we run the sparse sum algorithm. We first perform the communication operations, which are row-wise or column-wise broadcasts, and then it is followed by local multiplication. When this is over, the partial results for the output matrix are merged, and the entries that do not meet a certain criteria are pruned. We then perform the inflation and the normalization, which are computational cheap compared to the expansion. So at the right, you can see the respective linear algebra operation for a single MCL of the for a single iteration of the MCL algorithm. As you can see, the entire process can be expressed through operations on sparse matrices. So the main components of the CPU workflow are illustrated here at the left. We engineered this workflow with accelerator support for systems with accelerator support following a CPU-GPU joint workflow. This is because when the clustered network is large, which usually is the case, we need a lot of memory, which is quite constrained on GPUs. So we try to use GPUs for the most computational expensive parts, and we reserve the CPU for memory intensive or computational cheap components. So our contribution for this workflow can be grouped under three titles. First, I'm going to go over a pipeline sparse sum algorithm to perform distributed multiplication using both the CPU and GPU resources. I'm going to then introduce a novel binary merge algorithm to perform the merging of the partial results for the output matrix. And this is going to enable several optimizations that will, which are further going to improve the performance. Finally, we tackle the memory requirement estimation, then approximate algorithm. So we naturally offload the most computationally expensive component, the numeric multiplication, to the GPU, and hold CPU responsible for communication and partial result accumulation. So note that the sparse sum algorithm proceeds in stages. Hence, while GPU is busy performing the multiplication of the current iteration, the CPU can proceed to the next stage and prepare the matrices for the next multiplication that's going to be used in the next iteration. So this is illustrated in the figure below, where here BI and MI respectively denotes the broadcast and multiplication at stage I. So while let's say the GPU is busy with the multiplication in second stage, which here indicated with M2, the CPU can go ahead and perform the broadcast in the next stage, which here indicated with B3. So the host memory is used for storing the partial results produced by the GPU. At the end of the sparse summa, these results are merged to get the final results. So we associate this task with the CPU because it requires a lot of memory to store the partial results. So when the local multiplication is performed by the GPU, the host produces input matrices via broadcast operations. and the device multiplies them and generates intermediate results or the partial results for the host, which then stores them and then merges them. As soon as the input matrices are transferred to the device, the CPU can free the memory occupied by these matrices and continue on to prepare the inputs for the next stage. So in this way, the CPU only needs to wait for the transfer of the input matrices and not the multiplication itself, and then it can proceed into the next stage. In this way, we can reduce the time required for the multiplication in stage K and broadcast in stage K plus 1 to the maximum of those summed by the host-to-device transfer time. There are two important criteria in selecting how to perform the multiplication. These two metrics are flops and the compression factor. The flops metric is just used to decide whether to perform the multiplication on GPU or CPU. So if there are not enough arithmetic operations to saturate the GPU threads, we perform multiplication on CPU. Otherwise, we perform it on GPU by selecting an appropriate library according to the compression factor. So this compression factor is the average number of operations per output non-zero, and it indicates the arithmetic intensity. According to the compression factor, the performance can change, and there are different libraries that perform this task on GPUs according to different data structures they use. So some data structures are more well suited to matrices with high compression factor, multiplications with high compression factor. Some of them are suited to with multiplication with low compression factor. So the hybrid method here dynamically determines the multiplication algorithm, and it is able to achieve a 3-point twist without compared to the CPU-only version. CPU can still be idle if multiplication time dominates the communication time. So there is another optimization opportunity in keeping both the GPU and the CPU busy. This is by performing, this is achieved by performing the merging of the partial results on CPU by performing the local multiplication on GPU. So the idea here is that we can start merging the partial results on CPU in an incremental manner without needing to wait for all these to do the merge. So in this way, the computations for the merging can be overlapped with the multiplications, and these merges are often cheaper than the local multiplication in HipMCL. So we can do this merge immediately when, as soon as an intermediate result list becomes available or a partial result set becomes available. Although this is modest in terms of memory usage compared to the multi-way merge, immediately merging results performs many redundant passes over the results, and it also continues to occupy the CPUs, which are also tasked with relatively more expensive broadcast operations. So taking these issues into consideration, we propose a cheaper alternative called binary merge, which merges the intermediate results only in certain stages of the algorithm. So this algorithm has the same structure of the merge sort algorithm. The basic difference is that since the lists come in order as they become available, the algorithm cannot follow a divide and conquer design. So here the partial results are illustrated in these circles here, and there are 8 of them here indicated A, B, C, D, E, F, G, H. These partial results are produced by the GPU and they are transferred to the CPU memory. CPU can merge them immediately, as I mentioned, but this is going to perform a lot of redundant passes, and it's going to be quite expensive. So on the right is a binary merge in which we trigger a multi-way merge operation when a partial result set becomes available in certain stages. So we trigger a merge operation according to the stage ID in the sparse command. For example, when here B becomes available, we just merge them. F becomes available, we just merge them. However, when D becomes available, we perform a 3-way merge, including A, B, C, and D. Similarly, we perform a 4-way merge when H becomes available. Here, observe that the merge set sizes might differ drastically. So this the performance of this binary merge is evaluated in runtime and memory. So the multi-way merge here is the original algorithm that's used in HipMCL, and the binary merge is the one that I just described. So they both exhibit very similar runtime performances. The binary merge is only up to 5% slower than the multi-way merge. These are also in line with the runtime complexities of these two schemes. In terms of the memory usage, for the multi-way merge, it is simply given by the total number of elements that are merged. For the binary merge, however, since the merge operations are spread across the stages, its memory requirement is determined by the merge that contains the maximum number of elements, which is typically the merge in the final stage. Note that here, if the elements to be merged had all distinct keys, the binary and the multi-way merge would have the same memory overhead. However, this is usually not the case. And for this reason, the binary merge here can lead savings in the memory consumption. So it has up to 25% savings in terms of memory consumption. It's important because the algorithm uses a lot of memory, and these savings matter a lot in terms of parallel performance. So these two metrics, these figures regarding these two metrics show that apart from having roughly the same computational overhead, which can effectively be hidden by using the binary merge, the binary merge is also more efficient in terms of the memory usage. The final algorithm we have applied for is for another computational expansion step. It is symbolic multiplication. So HipMCL first needs to estimate the memory required prior to running an MCL iteration. So this estimation needs to be done at the beginning of each iteration, as the input network constantly changes across iterations. So this is an expensive operation. So it becomes a bottleneck after we have handled the other portions, ported them onto GPU or proposed another algorithms. So this estimation is originally done with a symbolic multiplication. So this inherently necessitates less memory compared to the numeric multiplication. However, it's expensive. It is complex is order of flops, floating point operations, and most of the challenges related to numeric multiplication still exist for the symbolic multiplication as well. Since we are just estimating the amount of memory, we need not to be exact, and we can just approximate the memory we need. So it's a reasonable assumption, and for this purpose, we adopt an approximate method. So this method makes use of the layered structure of the multiplication by capturing it with a two-layer graph. So it assigns random keys following an exponential distribution in the first layer, and then it propagates the smallest keys across these layers. So the gist of this method is that for a vertex field that is not for a vertex field that is in any layer other than the first layer, there's a correlation between the number of first layer vertices that reach V and the key of the minimally ranked vertex among them. So this is similar to the idea in min hash. So this operation can be seen as a sparse matrix dense matrix multiplication, where we overload the operators. So instead of multiply and add operators, we have a select second, which selects the dense matrix elements, and then a min operator for the addition. So the runtime of this estimation algorithm is R, number of keys, multiplied by the summation of the non-zeros in matrices A and B. So it has several advantages. First, when compression factor is large, this is expected to be faster than the exact estimation. It is easy to parallelize. And third, its memory requirements are quite modest. So we evaluate this the performance of probabilistic memory requirement estimation in terms of its accuracy and runtimes. In terms of accuracy, as you can see, by using relatively a few number of keys, around 7 to 10. Here, R means the number of keys that are used for the approximate algorithm. we can get an estimation that is within 10% range of the correct estimation. At the bottom figures, we compare the cumulative runtime spent in the exact computation, the exact estimation, which you see here with the dashed black line. Here, the probabilistic scheme is faster compared to the exact scheme due to its constant factor that does not change throughout the MCL iterations. Here, comparison between the compression factor and R, the number of keys, number of samples, explaining the runtime differences between these two estimation schemes is useful, where in the earlier iterations we have a very high compression factor. As you can see here, the approximate method is faster. However, as the iterations evolve, since the compression factor gets quite small, around 1 to 2, it tends to be faster. The exact estimation tends to be faster. So what happens when we put all these things together? So we compare this GPU-enabled HipMCL with the baseline HipMCL that only uses CPUs. At the right figure, we compare the performance of these two software in a network, on a network with 35 million proteins and 17 billion edges. So we use 100 summit nodes for those. And as you can see, the GPU-enabled HipMCL is able to achieve up to 12.4 speed up over the CPU-only HipMCL. We also run this GPU-enabled version for two larger protein similarity networks on Summit. So we present the clustering times regarding the baseline HipMCL. Those were run on not Summit, but Cori. So these were reported on Cori. So we did not run those on Summit again because that would take a lot of time. It's not a fair comparison, but it gives an idea how much resource and time would be necessary on a recent system with GPUs versus a relatively older system with no GPUs. So here, as you can see, there are two networks. The isolate network is more dense compared to the meta-class network. And in the isolate network, the GPU-enabled HipMCL just clusters the protein network in 15 minutes compared to using 2K nodes on Cori and having a time of 2.5 an hour. So as my conclusions, the applications are complex and they consist of several different components, and these different components can have different characteristics. So we have investigated such an application, the Markov clustering, which contains sparse data structures with significant communication overheads and a lot of irregular memory accesses. In order to take full advantage of the hardware, we propose ways to how to exploit both the GPU and CPU resources. And we presented new algorithmic techniques to take full advantage of the underlying hardware. So this concludes my presentation. If you have any questions, I would be happy to answer that.